An ion is an atom or molecule in which the total number of electrons is not equal to the total number of protons, giving the atom a net positive or negative electrical charge. Ions can be created by both chemical and physical means. In chemical terms, if a neutral atom loses one or more electrons, it has a net positive charge and is known as a cation. If an atom gains electrons, it has a net negative charge and is known as an anion. An ion consisting of a single atom is an atomic or monatomic ion. If it consists of two or more atoms, it is a molecular or polyatomic ion. In the case of physical ionization of a medium, such as a gas, what are known as ion pairs are created by ion impact, and each pair consists of a free electron and a positive ion. History of discovery. The word ion is the Greek a 1/4 degree I y 1/2, ion, going, the present participle of a 1/4 degree I 1/2 I plus or minus I to the first, ionai, to go. This term was introduced by English physicist and chemist Michael Faraday in 1834 for the then unknown species that goes from one electrode to the other through an aqueous medium. Faraday did not know the nature of these species, but he knew that since metals dissolved into and entered a solution at one electrode, and new metal came forth from a solution at the other electrode, that some kind of substance moved through the solution in a current, conveying matter from one place to the other. Faraday also introduced the words anion for a negatively charged ion, and cation for a positively charged one. In Faraday's nomenclature, cations were named because they were attracted to the cathode in a galvanic device and anions were named due to their attraction to the anode. Characteristics: ions in their gas-like state are highly reactive, and do not occur in large amounts on Earth, except in flames, lightning, electrical sparks, and other plasmas. These gas-like ions rapidly interact with ions of opposite charge to give neutral molecules or ionic salts. Ions are also produced in the liquid or solid state when salts interact with solvents to produce elevated ions, which are more stable, for reasons involving a combination of energy and entropy changes as the ions move away from each other to interact with the liquid. These stabilized species are more commonly found in the environment at low temperatures. A common example is the ions present in seawater, which are derived from the dissolved salts. All ions are charged, which means that like all charged objects they are attracted to opposite electric charges, repelled by like charges, when moving, travel in trajectories that are deflected by a magnetic field. Electrons, due to their smaller mass and thus larger space-filling properties as matter waves, determine the size of atoms and molecules that possess any electrons at all. Thus, anions are larger than the parent molecule or atom, as the excess electron, s, repel each other, and add to the physical size of the ion, because its size is determined by its electron cloud. As such, in general, cations are smaller than the corresponding parent atom or molecule due to the smaller size of its electron cloud. One particular cation contains no electrons, and thus is very much smaller than the parent hydrogen atom. Anions and cations. Since the electric charge on a proton is equal in magnitude to the charge on an electron, the net electric charge on an ion is equal to the number of protons in the ion minus the number of electrons. An anion, from the Greek word a 1/4 I 1/2 I per mil, meaning up, is an ion with more electrons than protons, giving it a net negative charge. A cation, from the Greek word I plus or minus I, meaning down, is an ion with fewer electrons than protons, giving it a positive charge. There are additional names used for ions with multiple charges. For example, an ion with Aa2 charge is known as a dianion and an ion with a +2 charge is known as a dication. A zwitterion is a neutral molecule with positive and negative charges at different locations within that molecule. Natural occurrences. Ions are ubiquitous in nature and are responsible for diverse phenomena from the luminescence of the Sun to the existence of the Earth's ionosphere. Atoms in their ionic state may have a different color from neutral atoms, and thus light absorption by metal ions gives the color of gemstones. In both inorganic and organic chemistry, the interaction of water and ions is extremely important. An example is the energy that drives breakdown of adenosine triphosphate. The following sections describe contexts in which ions feature prominently. These are arranged in decreasing physical length scale, from the astronomical to the microscopic. Astronomical. A collection of non-aqueous gas like ions, or even a gas containing a proportion of charged particles, is called a plasma. Greater than 99.9% of visible matter in the universe may be in the form of plasmas. These include our Sun and other stars and the space between planets, as well as the space in between stars. Plasmas are often called the fourth state of matter because their properties are substantially different from those of solids, liquids, and gases. Astrophysical plasmas predominantly contain a mixture of electrons and protons. Related technology: ions can be non-chemically prepared using various ion sources, usually involving high voltage or temperature. These are used in a multitude of devices such as mass spectrometers, optical emission spectrometers, particle accelerators, ion implanters, and ion engines. As reactive charged particles, they are also used in air purification by disrupting microbes, and in household items such as smoke detectors. As signaling and metabolism in organisms are controlled by a precise ionic gradient across membranes, the disruption of this gradient contributes to cell death. This is a common mechanism exploited by natural and artificial biocides, including the ion channels gramicidin and amphotericin. Inorganic dissolved ions are a component of total dissolved solids, an indicator of water quality in the world. Detection of ionizing radiation. The ionizing effect of radiation on a gas is extensively used for the detection of radiation such as alpha, beta, gamma and X-rays. The original ionization event in these instruments results in the formation of an ion pair. A positive ion and a free electron, by ion impact by the radiation on the gas molecules. The ionization chamber is the simplest of these detectors, and collects all the charges created by direct ionization within the gas through the application of an electric field. The Giga-1 1/4 layer tube and the proportional counter both use a phenomenon known as a Townsend avalanche to multiply the effect of the original ionizing event by means of a cascade effect whereby the free electrons are given sufficient energy by the electric field to release further electrons by ion impact. Chemistry, notation, denoting the charged state. When writing the chemical formula for an ion, its net charge is written in superscript immediately after the chemical structure for the molecule atom. The net charge is written with the magnitude before the sign. That is, a doubly charged cation is indicated as 2+ instead of +2. However, the magnitude of the charge is omitted for singly charged molecules atoms. For example, the sodium cation is indicated as Na+ and not Na1+. An alternative way of showing a molecule atom with multiple charges is by drawing out the signs multiple times. This is often seen with transition metals. Chemists sometimes circle the sign. This is merely ornamental and does not alter the chemical meaning. All three representations of Fe2+ shown in the figure are, thus, equivalent. Monatomic ions are sometimes also denoted with Roman numerals. For example, the Fe2+ example seen above is occasionally referred to as Fe2, or Fe-ii. The Roman numeral designates the formal oxidation state of an element, whereas the superscripted numerals denotes the net charge. The two notations are, therefore, exchangeable for monatomic ions, but the Roman numerals cannot be applied to polyatomic ions. However, it is possible to mix the notations for the individual metal center with a polyatomic complex, as shown by the uranyl ion example. Subclasses: if an ion contains unpaired electrons, it is called a radical ion. Just like uncharged radicals, radical ions are very reactive. Polyatomic ions containing oxygen, such as carbonate and sulfate, are called oxyanions. Molecular ions that contain at least one carbon to hydrogen bond are called organic ions. If the charge in an organic ion is formally centered on a carbon, it is termed a carbocation or carbanion. Formation of monatomic ions. Monatomic ions are formed by the gain or loss of electrons to the valence shell in an atom. The inner shells of an atom are filled with electrons that are tightly bound to the positively charged atomic nucleus, and so do not participate in this kind of chemical interaction. The process of gaining or losing electrons from a neutral atom or molecule is called ionization. Atoms can be ionized by bombardment with radiation, but the more usual process of ionization encountered in chemistry is the transfer of electrons between atoms or molecules. This transfer is usually driven by the attaining of stable electronic configurations. Atoms will gain or lose electrons depending on which action takes the least energy. For example, a sodium atom, Na, has a single electron in its valence shell, surrounding two stable, filled inner shells of 2 and 8 electrons. Since these filled shells are very stable, a sodium atom tends to lose its extra electron and attain this stable configuration, becoming a sodium cation in the process, Na++A. On the other hand, a chlorine atom, Cl, has 7 electrons in its valence shell, which is one short of the stable, filled shell with 8 electrons. Thus, a chlorine atom tends to gain an extra electron and attain a stable 8-electron configuration, becoming a chloride anion in the process, Cl plus A ℏ. This driving force is what causes sodium and chlorine to undergo a chemical reaction, wherein the extra electron is transferred from sodium to chlorine, forming sodium cations and chloride anions. Being oppositely charged, these cations and anions form ionic bonds and combine to form sodium chloride, NaCl, more commonly known as table salt. Na++ Cl NaCl, formation of polyatomic and molecular ions. Polyatomic and molecular ions are often formed by the gaining or losing of elemental ions such as a proton, H+, in neutral molecules. For example, when ammonia, NH3, accepts a proton, H+, a process called protonation, it forms the ammonium ion, NH4+. Ammonia and ammonium have the same number of electrons in essentially the same electronic configuration, but ammonium has an extra proton that gives it a net positive charge. Ammonia can also lose an electron to gain a positive charge, forming the ion NH+, 3. However, this ion is unstable, because it has an incomplete valence shell around the nitrogen atom, making it a very reactive radical ion. Due to the instability of radical ions, polyatomic and molecular ions are usually formed by gaining or losing elemental ions such as H+, rather than gaining or losing electrons. This allows the molecule to preserve its stable electronic configuration while acquiring an electrical charge. Ionization potential. The energy required to detach an electron in its lowest energy state from an atom or molecule of a gas with less net electric charge is called the ionization potential, or ionization energy. The nth ionization energy of an atom is the energy required to detach its nth electron after the first Na1 electrons have already been detached. Each successive ionization energy is markedly greater than the last. Particularly great increases occur after any given block of atomic orbitals is exhausted of electrons. For this reason, ions tend to form in ways that leave them with full orbital blocks. For example, sodium has one valence electron in its outermost shell, so in ionized form it is commonly found with one lost electron, as Na+. On the other side of the periodic table, chlorine has 7 valence electrons, so in ionized form it is commonly found with one gained electron, as Cl. Cesium has the lowest measured ionization energy of all the elements and helium has the greatest. In general, the ionization energy of metals is much lower than the ionization energy of known metals, which is why, in general, metals will lose electrons to form positively charged ions and known metals will gain electrons to form negatively charged ions. Ionic bonding. Ionic bonding is a kind of chemical bonding that arises from the mutual attraction of oppositely charged ions. Ions of like charge repel each other, and ions of opposite charge attract each other. Therefore ions do not usually exist on their own, but will bind with ions of opposite charge to form a crystal lattice. The resulting compound is called an ionic compound, and is said to be held together by ionic bonding. In ionic compounds there arise characteristic distances between ion neighbors from which the spatial extension and the ionic radius of individual ions may be derived. The most common type of ionic bonding is seen in compounds of metals and known metals. Metals are characterized by having a small number of electrons in excess of a stable, closed-shell electronic configuration. As such, they have the tendency to lose these extra electrons in order to retain a stable configuration. This property is known as electropositivity. Non-metals, on the other hand, are characterized by having an electron configuration just a few electrons short of a stable configuration. As such, they have the tendency to gain more electrons in order to achieve a stable configuration. This tendency is known as electronegativity. When a highly electropositive metal is combined with a highly electronegative nonmetal, the extra electrons from the metal atoms are transferred to the electron-deficient nonmetal atoms. This reaction produces metal cations and nonmetal anions, which are attracted to each other to form a salt. Common ions, see also. References